Okay, gang. In Chapter 7, we're going to take everything we've learned thus far and start applying it to real-world situations and coming up with the required pump discharge pressure in order to get the appropriate GPMs on the fire. Our objectives: explain the variables that must be considered in order to operate a pump at the maximum efficiency on the fire ground. Discuss the use of the required pump discharge pressure formula and its application to various pumping configurations. 3. Explain the development of the required pump discharge problem formula. Determine the RPDP for single lines at ground level. Solve problems to determine the RPDP for a single line wide into two lines at ground level, and determine the RPDP for layouts of Siamese lines, which is joining two lines into a single line at ground level. Solve problems to determine the required pump discharge pressure for lines laid uphill. Solve problems to determine the RPDP for lines laid downhill. Determine the RPDP for lines laid into the standpipe system. Determine the RPDP for lines laid into portable monitors. And determine the RPDP for lines laid into deck guns. Solve problems to determine the RPDP for lines laid into ladder pipes. And solve problems to determine the RPDP for lines laid into an aerial platform or other elevated master stream device. The friction loss problems in Chapter 6 considered only friction loss in the hoses. Therefore, the problems could be solved entirely by using the friction loss formula. This chapter considers hose layouts and configurations involving the need to solve for discharge and those involving elevation and appliances. The formulas introduced in this chapter is a pencil and paper formula. It is referred to as the required pump discharge pressure formula. The pump discharge pressure must be sufficient to provide the pressure losses due to nozzle pressure, friction loss in the hose, back pressure, forward pressure, and appliance friction loss. Essentially, you're going to add everything up and come up with one single number that is required in order to get the appropriate pressure in gallons per minute at the end of a hose line. The commonly accepted formula for determining the pump discharge pressure is as follows. Pump discharge pressure equals NP plus TPL. PDP, of course, is our pump discharge pressure. NP is our nozzle pressure in PSI. And TPL is our total pressure loss. And that includes such things as friction loss in hoses that we determined last chapter, pressure loss due to appliances, and we'll give you set numbers for that, and your pressure loss as well as gain due to elevation. It's important to know that you may not have all these variables on one problem, or you may have all of them. It just depends on the given pumping scenario and situation. Now, back pressure refers to those situations where the nozzle is being discharged at a point above the pump. So that would be like going up 2 stories or 3 stories and having the water flowing from an end of a nozzle line. So when these situations are encountered, you need to use 0.5 psi for each foot of head, meaning head is the vertical distance above the pump where the nozzle is being used. Appliance friction loss refers to the loss of pressure as the water flows through fittings such as reducers, increasers, manifolds, Siamese, Y, standpipes, portable monitors, and aerial apparatus. For the purpose of solving problems, you won't have to consider any friction loss whenever you're flowing less than 350 gallons per minute. So remember this rule when you're doing your math problems. When the flow is greater than 350 gallons per minute, a loss of 10 psi is used. So basically meaning you have to add 10 psi to your, of course, discharge pressure to get the correct answer. An exception is the friction loss for the master stream appliance. In these appliances, the loss is going to be 25 psi, not 10. And that is considered a standard regardless of the flow. Forward pressure is the term used to identify a situation where the discharge from a nozzle takes place at a location below the pump. So essentially we're going to be gaining pressure. And you should use the formula of 0.5 psi per each foot. Again, head is the vertical distance below the pump that the nozzle is being used. If a single line taken off a pumper is used to apply a single nozzle tip, the pressure produced by the pump will need to be sufficient to provide for the nozzle pressure and the friction loss in the hose. If several lines are taken off a pumper and provided with individual tips, the required pump discharge pressure for each of these lines must be calculated individually, which may result in the required pump discharge pressure on one or more of these lines being less than the required pump discharge pressure, which is the one that's going to be the highest. And then you have to, again, gate down or feather down the other two lines. If a constant flow or constant pressure nozzle is used in a problem, it is only necessary to solve for the friction loss in the hose layout and add the result to the nozzle pressure to solve the problem. However, if a smoothbore tips are used in the same type of problem, it is necessary to determine the amount of water flowing before the friction loss in the hose can be determined, because we have to know the gallons per minute. And for our fog or combination nozzles, you're going to have a set GPM of about 100 psi and 1,000 gallons per minute. Now, if it's a smooth tip, then we're going to have to use the 29.7 times diameter squared times square root of nozzle pressure to figure the gallons per minute, so we can back figure our friction loss. Now, here's some constants that you're going to need to know to figure out your math problems. The standard established for hand lines with a smoothbore tip is 50 psi, meaning that you have to have 50 psi at a hand line with a smoothbore tip. Now, you'll need 80 psi for master streams with a smoothbore tip. And then fog nozzles will either be 100, 75, and 50 psi nozzles are available. And again, that just depends on what the problem tells you. But as a rule of thumb, nozzle pressure on a fog nozzle must be 100 psi. Ground level problems require pump discharge pressure problems involving lines laid at ground level and can be divided into three principal categories. You're either going to have single lines that turn into two lines, or two lines that turn into one single line, and those are known as Siamese. Single lines. The solution to require pump discharge pressure problems where single lines are in use at ground level involves the following. You have to determine the nozzle pressure, and again, we give you those on the previous slides. You need to solve for the friction loss in the hose and the nozzle pressure to the friction loss in the hose. Then you're going to add it all up, and that will give us our required pump discharge pressure. So let's look at our first problem. Engine 6 is pumping through 400 feet of a single 1.5 inch hose that is equipped with a 5/8 inch tip. What is the required pump discharge pressure if the nozzle pressure is 50 psi? And look at figure 8.2. So your problem is going to look like this. Here's our 5/8 tip at 50 psi. We have 400 feet of 1.5 inch hose. So the first thing we need to figure out is how many gallons per minute are we flowing. Again, to do that, we're going to use our formula of 29.7 times the diameter square times the square root of pressure. They gave us the pressure of 50. So 29.7 times 5/8 of an inch square, or 0.625, just divide the 5 by the 8, and our pressure of 50. So we plug everything in, and we get that we are flowing 82.02 gallons per minute. So that's the first step. Now we got to figure out the friction loss going through the line while we're flowing 82.02 gallons per minute. And I always tell people, to me, it's easier if we start at the nozzle and work our way back, figuring all the various components. And then, of course, add them all up at the end. So now our friction loss is our coefficient, remember from our last chapter, times gallons per minute square. Again, we're dividing that by 100. And our length of hose, which was again divided by 100. So 0.82 square, so 0.82 times 0.82 times 4 times 24 gives us a friction loss in the hose of 64.55. So now solve for the required pump discharge pressure, which is the friction loss that we just figured plus the nozzle pressure that they gave us at the beginning. We add them both together and we get 114.55 psi. Our next question. We have 300 foot of 1 3/4 attack line. It has been laid at a single family house fire. The line is equipped with a constant gallonage 175 gallons per minute fog nozzle rated at 75 psi. So they're telling us that again we're going to be flowing 175 gallons per minute, so that's known. And we know we have a fog nozzle, and we have to already start at that end, working our way back, so we know it's going to be 75 psi plus the friction loss. So now let's figure the required pump discharge pressure for this layout. So now we're going to be looking at our friction loss for 300 feet of 1 3/4 line flowing 175 gallons per minute. So we're going to plug everything in. We again look up at our coefficient. Because remember, our problem is coefficient times GPM squared times length of hose. Again, both of those are divided by 100. So that's 15.5 times 1.75 squared times 3. So our friction loss for this problem is going to be 142.41. Now we got to add that to the nozzle pressure, which was 75, and they gave us that in our original question. So 75 plus 142.41 equals 217.41 psi, which is our required pump discharge pressure. So now let's look at our single line Y, which is one line, the larger line divided into two smaller ones. In a Y appliance, the flow from a single line again is divided into two or more lines. If the lines after the Y are the same length and the same size, then again, we only have to measure one side because it's going to be the same on both, because a Y considered to divide the water evenly. If it is more than 350 gallons per minute, because this is considered an appliance, a Y is appliance, then we're going to have to add an additional 10 psi to that pump discharge pressure to get the correct answer. So let's put all our steps together. You're going to figure the friction loss for one of the lines after the Y. Next, figure the friction loss in the supply line, and then add the friction loss from one of the smaller lines and the friction loss from the supply line to the appliance to get our required pump discharge pressure. So let's go through one together. Engine 10 has laid a 550-foot line of single 2.5-inch hose that has been wide into 2 1 3/4 lines. Each have 250 feet in length. Both lines, and they're being nice to us this time, are equipped with nozzles with a flow of 125 gallons per minute at 100 psi nozzle pressure. So we know our gallons, we know our pressure, so that's a good place to start. So now we got to figure out what the required pressure is. So if you're writing our layout, it's going to look something like this. The flow of 125 gallons per minute at 150 psi out of both. There is your supply line, 550 feet of 2.5. So remember now, we're going to have to add the 125 together, so that gives us 250 gallons per minute of water flowing to these lines. So that is going to come into play here when we figure out our friction loss for the supply line. So figure the friction loss in one of the 1 3/4 lines and the friction loss in the 2.5 line. Add those together and put in our required nozzle pressure that they gave us. And add the appliance friction loss if it's more than 350 gallons per minute. Remember, since that's a Y, if it's more than 350 gallons total, which it's not, you'll have to add 10 psi. So our nozzle pressure they gave us is 100 psi. Your friction loss is going to be 129.3 psi. And then, of course, you add those together, and that gives us 229.3 psi. Remember to figure our friction loss. It's our coefficient times gallons per minute. Of course, that's divided by 100 and then squared times length of hose divided by 100. And then you get that for the attack line and then the friction loss for the supply line. We add those together. You should get 129.3. And then, of course, we add that to our nozzle pressure, which gives us, again, our required pump discharge pressure. Siamese lines into a single line. The coefficients can be found in Table 7.1 and are used for problems involving Siamese lines of equal length. Here's a copy of your coefficients for using Siamese lines. Siamese lines into a single line. The friction loss in Siamese lines is approximately 1/4 that in a single line of the same size. So let's look at our problem. You have two 700-foot length of 3-inch hose with the 2.5-inch coupling having been laid from engine 5. The two lines having been Siamese into a single 2.5-inch line that is 250 feet in length. The line is equipped with a selectable gallonage nozzle set at 175 GPM with a minimum of 100 psi nozzle pressure. So what is the required pressure? So our problem is going to look something like this. So a Siamese layout is the one where the flow from two or more lines convert into the flow of one line. So first you need to determine the friction loss in the 2.5 inch line. Again, that's our supply line. So the friction loss is our coefficient off the chart times the gallons divided by 100 squared times the length of hose. So the friction loss is going to be 15.31. Next, you're going to solve the friction loss in the Siamese lines. And we're going to use the formula, but use the coefficient for the Siamese line instead. And we've got that at the beginning of this chapter, also in that chart. And that friction loss is going to be 4.29 psi. So now you add the two friction losses together. And since the flow is under 350 gallons per minute, there is no appliance friction loss. We don't have to add that additional 10 psi to get our answer. So now we solve for the required pump discharge pressure by adding the 100 and the 20 together. And you're looking at a required pump discharge pressure of 120 psi, or to be exact, 119.6 psi. Elevation and master string problems. The pressure created by 1 foot of head was introduced as P equals 0.434 times height. From this point on, we're going to really simplify it. So P is going to equal 0.5 times H, so it makes nice round numbers. So in addition, 5 pounds per floor is used for problems in multi-story buildings. So if you have one that's 5 stories up, then we know we're going to add an additional 5 pounds per floor. Don't count the first floor, so you're looking at, say 20 pounds per square inch as an example. Now, when we're looking at required pump discharge problems involving elevation and master streams, they can be divided into 7 principal categories: lines laid uphill, lines laid downhill, and if you remember about lines laid into standpipe systems. Required pump discharge problems involving elevation and master streams can be divided into 7 principal categories: lines laid into a portable monitor, lines laid into deck guns, lines laid into ladder pipes, and lines laid into aerial platforms or other elevated master stream devices. Now, lines laid up or downhill are generally said to be laid up or down a given grade. Grade is the vertical rise or decline over an elevation for every 100 feet of hose laid out. So up a 10% grade refers to the idea of the elevation rise of 10 feet per every 100 feet. Down, for example, a 15% grade means a decline of 15 feet for every 100 feet. And now you can figure the additional head pressure gain or loss on whether or not you go up or downhill. The solutions to required pump discharge problems when lines are laid uphill involve the following: determining the nozzle pressure, solve for the discharge if not given, solve for the head if not given, and then solve for the friction loss in the hose, and of course solve for the back pressure. So you basically have to do 5 different types of problems to come up with your single answer. Of course, then adding them all together to get it. So we add the nozzle pressure and friction loss in the hose and the back pressure to determine the required pump discharge pressure. This just adds one more part to the formula. Back pressure is figured in on this one. So our formula for a line laid uphill is nozzle pressure plus friction loss plus back pressure. Remember, we get 0.5 psi per foot of elevation. So let's look at our next problem. You have a single 2.5 inch line, 300 feet in length, that has been taken off a pumper and extends up a hill to a point 30 feet above the pumper, where it is pumped into operation. The line is equipped with a 1-inch tip operating at 50 psi nozzle pressure. What is the required pump discharge for this layout? Now there's a couple of things to keep in mind on this problem, and it will look something like this. Obviously you can see we've got the elevation to contend with. The other one is we've got to figure out how many gallons per minute we're flowing, because they did not tell us. So as I've said before, I like starting at the nozzle and working my way back. So our formula to figure out GPMs is 29.7 times the diameter square times the square root of pressure. And now that comes out to be 209.98 gallons per minute. With that being said, we can now figure out our friction loss. Our friction loss is going to be the coefficient, which you can find at the chart, times our gallons divided by 100. So that's going to be 2.09, or say 2.10 for round numbers, square, times, again, the length of hose divided by 100. And then we multiply all that together, we get our friction loss of 26.46. And now let's work on the elevation. So we know our back pressure is equal to 0.5 times the height in feet. So 0.5 times 30 feet high gives us a back pressure of 15 psi. And since we're going uphill, that's going to be an increase and not something that is going to add to our pressure. So now we add everything up. 50 for our nozzle pressure, 26.46 for our friction loss, and of course our 15 for our back pressure. So your required pump discharge pressure for this particular line is going to be 91.46 psi, or pounds per square inch. Next, we will do one with back pressure, but this will be up a 12% grade, which the gain is 12 feet of rise with every 100 feet. So if it's 200 feet worth of hose, then we know that we're going to actually have a height difference of 24 feet at the top, and so forth and so on. Remember, back pressure takes pressure away, but forward pressure adds pressure because we get that to gravity. And that's reminding us that going downhill, you're going to pick up pressure. So here's our problem. You have a single 3-inch line that's 400 feet in length with a 3-inch coupling that has been laid up a 12% grade. The 3-inch line has been wide into 2.5-inch lines, each having 100 feet in length. Both lines are equipped with a 5/8-inch tip at 50 psi nozzle pressure. So now, what is the required pressure? Okay, so a couple of things to keep in mind. One, we are going to have to figure our gallons per minute. Two, we're going to have to figure our friction loss in one of the 1.5-inch lines, since they're, again, of equal length and we're flowing the same thing, so we only have to figure one size. And then we're going to have to figure the friction loss in our supply line, which is the 400 feet of 3-inch. And then at the end of the day, we're going to have to figure out what our head pressure is going to be, because now we have a 12% grade of loss over 100 feet. And we're actually looking at a total of 500 feet. So we're looking at 12 times 0.5. So we're probably looking at what? 6? So like I said, let's start at the beginning. Our discharge, our gallons per minute, is 29.7 times the diameter square. So we turn 5/8 into a decimal. We times that by itself. Then we multiply that or the square root of 50 for nozzle pressure, and that gives us a reading of 82 gallons per minute. Next, we're going to figure out our friction loss in that 100-foot attack line. So we get our coefficient from our chart, which is 24. We know we're flowing 82 gallons per minute. So again, we divide that by 100. So that gives us 0.82. And then L is our length of hose divided by 100, which is 1. We multiply it all out, and we get a friction loss of 16.14. Now, we figure the friction loss in our supply line. Again, we get our coefficient from the chart, which is 0.667. We have to get our total gallons per minute, and remember, we've got to add both the attack lines together. And that gives us 164 gallons per minute. Then we divide that by 100, which gives us the 1.64. And then, of course, we multiply that by our length of hose, which is 400 feet. Again, divide that by 100, which gives us the 4. So our friction loss now is 7.28. So now we add all our friction loss together, and we have a total of 23.42 psi of friction loss. Now we got to figure out our head pressure. So we had our 12% grade, and we were going to do 0.5 per feet. So 60 times 0.5 in height, because again we're going up 12 feet per 100 feet. So I misspoke a little earlier, but so that's 12 per each 100 feet. We have 400 feet, so that gives us 60. And then 60 times 0.5 per foot, which gives us an additional head pressure of 30 psi we've got to figure out. So now we add everything together. We get our nozzle pressure that they gave us is 50. We figured the friction loss from both our supply and attack lines is 23.42. And now we add in that back pressure of 30. So our required discharge pressure equals 103.42 psi. So now let's look at lines laid downhill. And the solution to require to pump discharge problems when lines laid downhill can be figured as following. And it's very similar to our last one. The only difference is instead of subtracting the head pressure, you're going to basically add it. Or I should say you're going to subtract it as opposed to add it. So first you're going to determine the nozzle pressure. Then you're going to solve for the discharge if not given. Then you're going to solve for the head if not given. And then of course solve for the friction loss. And then solve for the forward pressure. So let's walk through one. Since forward pressure assists with gravity, the elevation in this case is subtracted from the required pump discharge pressure formula. So here's our problem. We have 550 foot length of an 1.5 inch hose that has been laid downhill from engine 9. The line is equipped with a 5/8 inch tip at 50 psi nozzle pressure. What is the required pump discharge pressure? Note the grade is not given in our problem, so consider it to be a 10% grade. So this is what our pumping scenario is going to look like. Notice our 550 feet of 1.5 inch, the 5/8 inch tip at 50 psi. So what are we going to have to pump at to get there? First, we need to know the gallons per minute, right? Then put the numbers into the friction loss formula for the hose to figure out what you need. Subtract the forward pressure from the friction loss and the nozzle pressure, and you get 111.26. So they gave us a nozzle pressure of 50. Our friction loss is going to be 88.76. So we add those two together, and then we subtract that gain, that head pressure gain that we're going to get of 27.5, and that gives us a required pump discharge pressure of 111.26. Okay, so here's another problem. The layout from engine 1 is down a 15% grade at 800 feet of single 3-inch hose equipped with 2.5-inch couplings, which has been reduced to 500 feet of 2.5-inch hose. The 2.5-inch line is equipped with a 1 1/8 inch tip at 50 psi. What is the required pump discharge pressure? Now we've got a couple of things to think about on this problem. Obviously, we know we're going to have to figure the gallons per minute. The other thing we got to look at is our 15% grade loss, and we've also got to look at this reducer that comes into play and see about our friction loss in it if we have enough gallons per minute to make it an issue. So first, our gallons per minute, which comes out to be 265.75 gallons per minute. Then we're going to figure our friction loss, and we have to do it for each section because we have different size hoses. So the friction loss is going to be our coefficient, which is 2 times the gallons divided by 100 square, which is 2.66, times the length of hose, again divided by 100, is 5. And that gives you a friction loss for our first line of 70.76. Next, we figure out the friction loss for our 3-inch line. Same way, the different coefficients, which is going to be 45.28. So the total friction loss for both lines is 116.04. Next, we're going to solve for the forward pressure. So we have 1,300 total feet with a 15% grade. So 13 times 15, and all we're doing is just, again, moving the decimal point over 2 spaces to get everything equaled out. And that gives us 195 feet, or again, you can do it the long way. So that's 195 feet of head, which equals 97.5 pounds per square inch. Because we're taking that 195 and we are multiplying it by 0.5 per foot. So our required discharge pump pressure is going to be the nozzle pressure of 50, the friction loss of 116, and we're going to subtract our elevation gain of 97.5, so that gives us a required pump discharge pressure of 68.54. So now let's look at lines laid into a standpipe system. Normally, one of the factors that need to be considered when lines are laid in the standpipe system is whether an allowance needs to be added for the friction loss of the standpipe system itself. So let's look at our problem. Lines have been laid into a standpipe with water flowing at a rate of 500 gallons per minute. The standpipe system is made up of 6-inch piping. Several lines have been taken off and are working on the 9th and 10th floor. What pump discharge pressure is needed for the friction loss in the standpipe? So our problem is going to look something like this, and now we're just trying to figure our friction loss for the standpipe. So to figure the friction loss, the same as in the hose, but the coefficient will be for a standpipe. And you can get your coefficient from a chart. So friction loss is our coefficient, which is 0.052. We know that our quantity, because it gives us that, between the two lines are 500 gallons per minute. So again, divide that by 100 gives us 5. And then our length of hose is actually going to be figured out by the number of floors. And then we're going to convert that to a decimal. Since this figures to just cover, or just over 1 pound of friction loss, we won't consider the friction loss in the standpipe. Remember though, if the flow is more than 350 gallons per minute, we should at least add 10 psi for the appliance. You will also have to consider the back pressure. So even though we don't have friction loss in the standpipe, we're going to consider an appliance, so we'll need to add 10 psi because we're over 350 gallons. And of course, we got to overcome our height problem. So the solution to required pump discharge problems when lines are laid into the standpipe systems involves the following. First, determine the nozzle pressure. Then solve for the discharges if it's not getting, or gallons per minute. Then you solve for your back pressure. Then we're going to solve for friction loss in the hose and consider whether the appliance friction loss needs to be added. So the equation we're going to use looks like this. Nozzle pressure plus friction loss plus back pressure plus appliance friction loss. And again, you may have all or just some of these depending on your variables. So we have our problem. We have a 1.25" tip attached to 100 feet of 2.5-inch hose is working on the 6th floor of a 10-story building. A single 3-inch line with a 2.5-inch coupling, 200 feet in length, has been taken off engine 7 and is supplying the standpipe. What is the required pump discharge pressure if the nozzle pressure is 50 psi? So it should look something like this. We have 200 feet of 3-inch with 2.5-inch coupling. We have a 6-inch standpipe. We have 100 feet of 2.5-inch with a 1.25" tip, and they're flowing 50 psi. Granted, we don't have to worry about this elevation. We don't have to worry up to the 7th floor. So again, first, how many gallons are we flowing a minute? 29.7 times the diameter square times the square root of nozzle pressure, which they gave us. So that gives us a total of 328.09 gallons per minute. Now you can solve for your friction loss. So, since we are working on the 6th floor, we need to include the back pressure. Since we are already on the 1st floor, we only need to figure for the first 5 floors. There are 5 pounds per square inch per floor. Essentially, we're saying it's 10 feet per floor for round numbers. So that gives us 5 psi per floor. So we are 5 floors up. So the back pressure now is 25 psi. Now you're going to figure your friction loss for each section of hose. So our friction loss for the 2.5-inch hose is as follows. Friction loss equals coefficient times gallons per minute square, of course, divided by 100, times the length of hose, also divided by 100. Our coefficient from our chart is 2. Our gallons per minute are 3.28, and our length of lay is only 1. So we multiply them all together, and we get an answer of 21.52. Now we figured the friction loss for the 3-inch hose. The friction loss formula is still the same. C, the coefficient, times the gallons per minute divided by 100 square, times the length of hose divided by 100. Our coefficient from the chart is 0.8. Our gallons per minute are still 328, so that gives us 3.28 for Q. And now our length of hose is going to be 2. We plug in our numbers, we do our math, and we get 17.21. So now we can add everything up from our nozzle pressure to our combination of our friction loss to the back pressure, which gives us the required pump discharge pressure of 113.73. So now let's look at lines laid into portable monitors. A portable monitor is one of several different types of appliances used to provide a master stream. A master stream is defined as any stream that is too large to be handheld or a stream producing more than 350 gallons per minute. Some monitors are available with smoothbore tips, generally of the stacked tip variety. Most, however, are equipped with a fog nozzle of various sizes and types. The monitors may be designed with a single inlet or dual inlet or a triple inlet, meaning basically it can be supplied by 2 or 3 lines. The solution to required pump discharge problems with lines that are laid to a supply portable monitor involves the following. First, determine the nozzle pressure. 2. Solve for the discharge, or gallons per minute if not given, and then solve for the friction loss in the hose. Since all portable monitors are designed as master stream appliances, then we've got to add that 25 psi in addition to the friction loss to get our required pump discharge pressure. So we add the nozzle pressure, the friction loss in the hose, and the 25 psi to get our final answer. So here's our math problem. A portable monitor is being supplied by 3 2.5-inch lines, each 350 feet in length. The monitor is equipped with an 1.75-inch smoothbore tip operating at 80 psi. What is the required pump discharge pressure? So your pumping scenario is going to look something like this. First thing we're going to have to look at and figure out is how many gallons per minute are we flowing, so we can then figure out the friction loss. So now we do 29.7 times our diameter square, which is 1.75 inches, times the square root of the nozzle pressure, which they gave us is 80. So we do our math and we come up with a whopping 813.15 gallons per minute. Now you're going to solve for the friction loss in the hose using the coefficient from the book for Siamese lines. Because remember, we're joining 3 lines into one. So that comes out to be 50.89 psi. So we've got our friction loss, we've got our nozzle pressure, and then we add an additional 25 for the appliance being the master stream. Add them all together, so your required pump discharge pressure should be 155.89 pounds per square inch on your pump panel. Deck guns are similar to portable monitors in design and style. However, the primary difference is that the deck guns are secured in place. This gives them the ability to withstand a much greater back pressure than a portable monitor. Often these things are secured to the fire truck. As you can see here at the top, here is the deck gun. And it appears in this particular photo that it is being supplied by one 5-inch line. Deck guns are supplied by 2 different methods. They may be supplied directly by the pumper to which they are attached or by a separate apparatus. Another type is supplied directly from the pump through a pre-piped arrangement on the apparatus. So the solution to required pump discharge problems when lines are laid to supply deck gun involve the following. First, determine the nozzle pressure, then solve for the gallons per minute, and then solve for the friction loss in the hose. Since the deck gun is a master stream, you add 25 for the appliance. The deck gun on engine 83 is equipped with a 2-inch smoothbore tip at 80 psi nozzle pressure. So what is our required pump discharge pressure? If you want, you can figure out the gallons per minute, but we really don't need to know it since it's a mounted deck gun. We know that we have to pump it at 80 psi to begin with. Then you just have to add the appliance loss of 25. So your required pump discharge pressure is only going to be 105 psi. Now it's going to be a little different in this case. Now we have lines led into a ladder pipe. There are two general types of ladder pipes in common use. One type is permanently attached to the ladder and is what we call pre-piped, with the fittings for supply and the unit located at or near the base of the ladder. The second type, however, is detachable and is supplied by a fire hose, which is usually a single 3-inch line that runs up the outside of the ladder or underneath and is fastened into place. Regardless of the type of ladder pipe, hydraulic calculation necessary to supply the units are the same. The solutions to required pump discharge problems when lines are laid to supply the ladder pipe involve the following. First, determine the nozzle pressure. Is it a smooth bore or a fog? Then solve for the gallons per minute, if not given, and then we look at our friction loss in the hose. Our next step, we have to solve for the back pressure because now we've got to look at our elevation. We can't forget that. And then, of course, we have to add 25 psi for our appliance. We also have to look at the pre-pipe units. They also receive an allowance for the friction loss in the piping. This allowance should come from the manufacturer. So essentially that's just depending on the manufacturer, another number we got to kick in for the friction loss to add it all up to. So let's figure our problem out. You have a pre-pipe ladder pipe in operation at a height of 75 feet above ground. It is equipped with a smooth bore 1.5-inch nozzle or tip operating at 80 psi. The unit is being supplied by two 3-inch lines with 2.5-inch couplings. Each line is 450 feet in length. The friction loss for the piping is 35 psi. So now, what is the pressure that is required at the pump supplying the hose lines? So your problem is going to look something like this. We have that 1.5-inch tip here, pumping at 80 psi. We are 75 feet in the air, and here's our supply. So we've got to figure out our friction loss for our supply. We have to add the friction loss for the height, and then the pre-piped allowance that they gave us in the other slide. Again, starting at the tip, how many gallons per minute are we flowing? And we get that by doing 29.7 times the diameter square times the square root of pressure. That gives us 597.42 gallons per minute after we do our math. Now you're going to solve for the friction loss in the hose. And the friction loss is our coefficient that we get from our chart times gallons per minute divided by 100 square times the length of hose divided by 100. So our friction loss is 32.08. Now we figure our back pressure, which is 0.5 times H. And our H, of course, is 75 feet. So 0.5 times 75 gives us a back pressure that we have to add is 37.5. So now we can finally add everything up and get our required pump discharge pressure. We know our nozzle pressure is 80. That was given to us. We added up all our friction loss, and that is 32.08. We figured our elevation loss or back pressure being 37.5. We also have to add in the appliance friction loss, since it is a master stream, of 25. And then finally, we add in our manufacturer friction loss for the piping, which is 35 as well. So you add it all up, and your required pump discharge pressure overall should be 209.58 psi. So let's look at our last type, lines laid into an aerial platform. First, you have to determine the nozzle pressure, then solve for the gallons per minute, again if not given, and of course solve for the friction loss in the hose. Add in the back pressure, add 25 for the appliance, and then add in for the pre-piping as per manufacturer recommendations. Here's an example of an elevated platform. So here's our math problem. You have an aerial platform that is equipped with an automatic nozzle having a flow range of 150 to 1200 gallons per minute and is operating at 100 psi nozzle pressure. It is a pre-piped system raised to a height of 80 feet. The friction loss for a pre-piped system is 40 psi. The plan is to supply the unit by one 5-inch line that is 300 feet in length. What is the required pump discharge pressure for this layout? So your problem is going to look something like this. So first, solve for the friction loss in the hose layout. So that's our coefficient for the 5-inch, which is 0.08 times the gallons per minute, which was 1200 because that was the most, the highest. And divide that by 100, so that's 12 times 12. And then our length of hose, which is 300 feet, divided by 100, of course, gives us our 3. So our friction loss is 34.56. Notice we're only figuring the friction loss right now from the supply hose, because they've already given us the friction loss for the piping going up. So the last thing we got to solve for is our back pressure. And we know that we're 80 feet up, so 80 times 0.5 gives us a back pressure of 40 psi. So now we add it all up. Our nozzle pressure, 100, plus our friction loss, plus our appliance friction loss, and our piping allowance that they gave us from the manufacturer. So that's 100 plus 34.56 plus the appliance plus the piping gives you a total of 239.56 pounds per square inch. Okay guys, so you have a lot of math problems to get cracking on, so get to work on them. If you have any questions, you can email me at aroberts@athenstech.edu or give me a call in the office, and we can run through and figure out where your mistake is. Make sure you show line by line what you're doing, because it makes it a whole lot easier to figure out what you did or did not do correctly, so we can get things figured out. So until next time, be safe, and you guys have a wonderful day.